Great pleasure to welcome you to the afternoon session of PETS, session on location privacy. I want a few housekeeping notes. The first is that we actually don't have a mic for the Q&A, so I'm going to ask all the speakers to repeat the questions and then answer the questions. And so with that, it's a great pleasure to introduce Rinku, who'll be talking about location privacy for rank-based geoquery systems.
Okay, so good afternoon. My name is Rinku Dewri. I'm with University of Denver. This work was done mostly by my student, Wissam Altarjaman, and my colleague at DU, Ramakrishna Thurimela. Wissam has graduated, so he's not here to give the talk anymore. So I'll present on his behalf here. I'm going to start with an application, a web application that we created just to motivate what is it that we're going to talk about. Let's see. Okay. So essentially, we're going to just do some kind of a Google search for some POI. So I'm just going to put, let's say, Indian food there. Just removing the space there because it switches to the next slide, but Google will take care of that. And then color hall UML. Okay. So this is going to show me Indian places I can get Indian food near this location. And so what we're looking at is, so we're using Google APIs for this, and we're listing down the top 10 places that Google, the APIs have returned, and that's what this left table is. Now, we can take a look at where those are located. Quickly, as just as a point there, if I just so this is India House, which basically is ranked at number 3 according to the results set that was returned. So as you can see here that Google is not ranking these matches just based on distance. It is using other kind of factors to also use in the ranking method. So what we're going to do is maybe move the query point, that red marker is where the current query point is. And then let me just take it out a little bit and see what the result set would be like when I do that. So you see, if I move it, and this is, I have moved it out around 1.2 miles, and we see that the result set is still the same, okay? Which again is a reinstatement of the fact that you were seeing results that are not dominated just by distance, but by other factors when this ranking is going on. And we can do this a little bit more. And you'll start to see changes because at some point the distance factor also dominates. Maybe somewhere here. Yeah, so on all directions you can move the pointer and then see that the result set is different. Of course, we don't know where the shift exactly happened. And it depends from keyword to keyword you search, and also depends on where you are located. Okay, so the factors that go into this kind of a ranking, I'm going to just list out 2 of those. There could be others. One is the density of objects. So you could have objects, the querying objects, being very sparse in the neighborhood where you are making the query. And so in that case, what happens is when you move, so when the query point is being moved around, the result set there really doesn't change a whole lot. You're looking for 10 here is something. There is only 10 of those, so you can move around a whole lot without really affecting the results. Okay. Other case would be you could have dense spread of the POI. So this could be something that you could find almost every block, maybe a cafe or whatever. So in this case, you can think that, yeah, if I move around, then the results that I get would be sensitive to my movement. So if I can move around the mile, and then things may change a whole lot. Okay. But then there is another factor that goes into retrieving this result set, which is the ranking function. And remember, the ranking function is not made up of only distance. It is also made up of what we call prominence factors. Okay? So other things that are used along with the distance. So as a result of which, this ranking function helps offset kind of like the sensitivity you get when you have sparse POIs, which means that when ranking functions are in play, you could move around a lot and still be only seeing the same results. So the sensitivity you get because of having a sparse POI distribution kind of is offset because of the use of other factors in the ranking. So given such ranking functions are in existence or in use, you can think of centering around you, there could be what we call zones. So what essentially means is that, so for example, we could find a zone wherein if you move around, the result doesn't change at all. So you get the same result set. Then there could be an adjacent zone where if you move around, if you go out into that zone, you still get to see most of the results that you would see in your actual location, but maybe one mismatch. So one of the points might be different now. So similarly, if you move out a little bit more, you could get two mismatches and so on and so forth. The whole idea being that the change is progressive in the sense that results do not abruptly change. I'm here, here's the top 10 result here. If I move 2 miles out, my result is all different. Doesn't really happen a whole lot, especially when ranking functions are in play here. So just to again, another kind of validation on that would be what this plot is showing is it's showing the results from doing, I think this was around 1 million queries around LA, and so we picked a point in LA to do a query. I think the query was for cafe or something, and then we picked a point within, if I remember correctly, within 2 kilometers of that query point. And then we checked, okay, what was the overlap in the result sets. So this kind of distribution is showing you, okay, well, where do you see? So essentially, what we are seeing is that even without doing any kind of technique, any kind of privacy preserving technique, if I just maybe randomly pick a point within a certain distance of where I am still will be able to see many of the correct results, or at least the same results that I would see if I use my true location. Okay? So the rest of what I'm going to talk about is to just make sure that this happens more often, and of course with some kind of a privacy bound. So I just don't want to give it out to chance. I want it so that it happens most of the time. Okay? So let me just give you a brief idea. I'm sure if you have worked in location privacy, you're familiar with this idea, but otherwise, what is this mechanism we are talking about? So think of the mechanism as some kind of a process that takes some kind of a hidden location. Of course, there are query parameters, other kind of parameters also there, and we consider all of those to be public knowledge. And then the mechanism spits out some output. The output could be another perturbed location from which the query will actually be made, and in our case, the output really is a mix of locations and sets and things like that. So you have some outputs that are being generated. And the idea is that from an adversarial point of view, the idea is to figure out what was the hidden input, what was the hidden location. We're talking about location privacy, given that you are observing certain outputs and that you know the mechanism, you know the parameters involved in the mechanism, all that kind of stuff. Okay. Now, to do that inference, the adversary could be using some kind of a background knowledge. So background knowledge could be prior knowledge that the adversary has on where a certain user is likely going to be, all that kind of stuff. Now, it's very difficult to tackle background knowledge because they assume something and then do your process based on that. So that's why we adopt a different kind of notion. Again, it's not us. It appeared in 2013. Costas is here somewhere. So the idea of geo-indistinguishability was proposed. So instead of looking at prior knowledge, we asked this question, okay, let's look at the output and ask the question, what are the chances that at different locations actually produce this particular output. Okay? And we're looking at the ratio of these probabilities given some two locations n and L prime, could be any locations, and S could be any output that the method generates. Then we say, and we call, let's say we call it the indistinguishability ratio or something like that. Okay? And then we say, okay, if this value is 1, essentially what it is saying is that that given S, there is no way, essentially it's independent of L. So there's no way you can figure out if L was used to generate S or L prime was used to generate S. Okay? Then, and as you move away from this point, you are saying that the locations are becoming more and more distinguishable. The ratio is basically going away from 1 at that point. Okay? So then as privacy mechanisms, what you can try to do is you can say, okay, I'm not going to allow this ratio to just go on and on forever on either side. I'm going to bound it to some limit. Okay? So on either side, we're going to say that the ratio is always going to be between those 2 points. Okay? Now, you can bound it to some fixed value, okay? Or as geo-indistinguishability does, they say, okay, let's bound it based on some property of the two locations, okay? And in which case, in geo-indistinguishability, that would be the distance between the two locations. So what it means is that if the locations are closer, then it will be more difficult for you to distinguish between basically compute, then the distinguishability ratio will be closer to 1 in that sense. So it will be more difficult for you to tell which location was used to generate the output the more closer they are. Okay? So moving on, we can now also talk about something similar, but instead of just using distance, we are going to say, okay, let's try to do that, but let's not just think of distance, let's just think of the similarity of results. So we will say that two locations will be more and more indistinguishable, ratio will be closer to 1, if they're producing similar results. Okay? So if they produce similar results, they'll be more indistinct. And that's what the idea is in this paper. We're just extending the whole idea from distance to other kind of functions. Okay. So then again, what we are going to say, what we are saying is that two locations in the same zone, so same zone means they produce the same result set, they should be indistinguishable. Okay? And then if you move out to a different zone, then the degree of distinguishability will depend on what kind of a mismatch or match is there between the two sets. Okay? If you like equations, that's how basically you state it. I would urge you to just go to the paper and take a look at that. But that's the whole idea, that essentially what we're trying to capture is the more similar two locations are in terms of results they produce, the more distinguishable we will say they will be. Okay. Now, it's not necessary that you think of or compare these locations just in terms of query results. You can use other kinds of functions also. We have not tried that. So you can say, okay, I want these locations to be distinguishable based on, I don't know, the demographics of the people staying there. So you can, accordingly, your function will be different in that case. Okay. So using this principle, we then develop the mechanism. That's more or less the core idea. We develop the mechanism to enforce it in terms of a POI search environment. So what the mechanism does is, I'll go through it quickly, it's kind of a multi-step process. It generates a perturbed location first of all. So we are somewhere in here. It will generate a perturbed location. You can do it uniformly. You can use geo-indistinguishability for that, whichever mechanism you use. You end up with some location that is not a true location. And then you do a big search around that location. Essentially, you say, well, give me all the POIs, relevant POIs in a big radius. Okay, and then what you retrieve at this point is minimal information. You can get like location and prominence data only. You don't get details of the POIs in this case. Okay, so you get that. Then we locally compute the ranks for all these POIs using that location and prominence information. And in the paper, we talk about the nature of the ranking function. Okay, if the ranking function is more or less linear, then you can club together. You can do this ranking without revealing what the function is also. Okay? Then you move ahead and you do a computation on the top K results at multiple points within a certain area surrounding your perturbed point. Okay, and then you assign a score. The score is assigned based on how much similarity there is between that point and then between a point and a true result set. So you basically match, do a set intersection and look at the overlap. Okay, and then we use a sampling method to pick one of these sets for as the final answer. Okay, and this sampling is done using the standard exponential mechanism. Essentially, you give exponentially higher weight to more high quality sets, and then you do a sampling, and you then retrieve the details on that sampling. And this is just showing you an idea about the probability of picking matches when you do this exponential sampling. Okay. So quickly, just cover for the results part. This is showing you the probability of you getting more number of matches in terms of the result set. We did a top 10 search here, and this data was generated for 15 different keywords across 5 different cities, overall around 750,000 different queries. Okay, and then the point here to take is that the chances of getting 8 or more matches is essentially you reach levels like 95% there. So there's 1 or 2 miss can happen there. Now, when you do miss them, you will see that the misses happen mostly in the lower ranked results. So it's not that you miss higher ranked entities, and that's what we are trying to show in here. This is basically the rank of the missed objects. Okay. Quick note on the timings, because there's local computation involved. Overall, the whole process is taking for a query around 2.5 to 3 seconds. Again, if you just do a regular query, it's going to take somewhere around 2.5 seconds anyways. Okay. Okay, I'll leave out this part. This is mostly a comparative study that we did with you in distinguishability. Okay, so conclusion-wise, I just want to highlight this point that the whole idea is the landscape of query results is often not just, it's often plateaued in places based on where the location in, where there's POI distribution, all this kind of stuff is. And the privacy methods we have seen till now doesn't exploit that. So it would be useful to exploit that particular plateaued nature of the landscape and design maybe stronger privacy mechanisms in future. Okay, thank you.